Coming up on this episode of the IoT Inc. Business Show.
I see it as a differentiator. So I see it as the fact that there's going to be lots of open data, there's going to be lots of data in general, there's going to be open source hardware and software and so on. And somehow someone's got to put it all together and make it do something which solves the real business problems. And that's where this all comes into play.
First it was big data, and now it's the Internet of Things. The science of data is becoming increasingly sexy. Well, maybe not Victoria's Secret sexy, but it certainly gets the juices flowing for those business leaders in the know. Hot or not? Definitely hot. In this episode of the IoT Business Show, I speak with Ajit Jaokar about his passion, data science, and the application of machine learning, deep learning, and predictive analytics in IoT.
All this and more on this episode of the IoT Inc. Business Show. The people, the business, and the technology of the next generation internet. This is the IoT Inc. Business Show. And now, here's your host, Bruce Sinclair.
Hello and welcome to the IoT Inc. Business Show. This show is made possible by sales of my book, IoT Inc., published by McGraw-Hill, and the IoT Inc. Certified IoT Professional, or ICIP, online training and certification program. Become a certified IoT professional by completing the program's 3 courses: ICIP Technology, ICIP Business, and ICIP Strategy and Digital Transformation. Details of which can be found at www.iot-inc.com. That's www.iot-inc.com.
With me today on episode 25 is Ajit Jaokar. Ajit is a researcher, entrepreneur, and academic. His current research focuses on applying data science algorithms to IoT applications, including predictive analytics, time series data, sensor fusion, and deep learning, and he teaches this at Oxford University and the Technical University of Madrid. Ajit, welcome to the show.
Thank you. Great to be here.
So, sensor fusion, huh? What exactly is that?
Okay, right. Now, the whole idea of sensor fusion is the fact that it's more than one sensors making a certain prediction. So, for example, if you consider an old people's home and you want to monitor some elderly people in a home, but you don't want to monitor this person all the time for obviously privacy reasons and so on. So what you then do effectively is have multiple sensors monitor different things, but no one sensor monitors the person all the time. So therefore, if you say that this person opens the fridge, takes the milk, goes to coffee, makes the coffee, puts on the TV, and so on. Therefore, all these activities have a certain prediction built into them. And therefore, if you combine the readings from all these sensors, you make a certain assessment if this person is okay or not. And therefore, it's an algorithmic reading based on multiple sensors. So this is possibly the best example of sensor fusion. And that applies to many scenarios, everything from oil rigs to the one I just mentioned.
Yeah. So sensor fusion, you could also call it data fusion, or would there be a difference?
Yes, I think the data fusion, when people talk about data fusion, they just mean combining different data sets, whereas what I mean here is more an algorithmic perspective, and that means not at various levels of the stack. So at one level, you have Fourier transforms and all the mathematical kind of stuff, which looks at various signals and converts them. And at other levels, you have different sensors giving readings and different at different levels, and you kind of merge them together. So it's a fairly complex domain. So it's more than just merging data. It's across the stack, is what I meant to say. Yeah.
Got it. Well, Ajit and I, we first met a couple months ago. We were both teaching different workshops at Internet of Things World. That was at Moscone Center in San Francisco. And it turns out that we're going to be both teaching different workshops, or the same workshops, but in a different location in Berlin in, I guess, a couple months from now. So obviously you have a lot of IoT experience, but maybe you can tell our listeners about yourself and your background in IoT.
Indeed. So what I started off, like many people in the IoT industry today, I started off with the telecom side of things. And within the telecom industry, I've been involved with various aspects of what is called machine to machine in the telecom world. And one of the projects I got involved in was smart cities, and that really involved specifically working with a specific city in the UK, which is Liverpool, which is about 2 hours north of London, and its claim to fame, of course, is the home of the Beatles. But other than that, of course, it's a dynamic place and a rapidly growing place, and so on. So I did some various projects around the city of Liverpool, which involve transportation, health, and generally under the umbrella of smart cities. And that's where I got into IoT. And of course, it wasn't really called IoT at that time. It is really more a specific project. But more importantly, I've been involved more specifically on the data analytics side of IoT. So I've always been involved into looking at how you can do things with the data. And that, I think, is a key differentiator from my perspective, from a business model point of view, from an innovation point of view, and so on. And so that's how I got into data science and IoT. Then, of course, I also transitioned my Oxford University course to do the same thing, to teach the same thing, to refocus on data science and IoT, which was not such a wide leap from what we were already doing with the telecoms world. Really what we did was we expanded the radio function, so not just a cellular function. We looked at all sorts of different radios, and we looked at different verticals, and then we looked at different data sets, and then applied the classic machine learning algorithms to those data sets. And that really is what I do and teach.
Machine learning, applying them to data sets. Now, in the telecom world, what was the analytics focused on?
In the telecom world, it's a little bit, it's a bit of a two-sided game. So on one hand, telcos have massive amounts of data, and that every telco will tell you that. The negative of that is that they really can't use it for anything much intended from what its original purpose was. So your telco, and that's the legal and the statutory thing as well. So it's very well, all countries have this thing that the telco may know a heck of a lot about you, but they are not supposed to reuse that information for a purpose other than what it was intended.
Right.
And therefore, you have a strange thing where you have lots of data, but most of the use cases tend to be more inward-looking, what I call it. So by inward-looking, they tend to be looking at churn reduction, or when the telco works with a specific vendor, it's more of a B2B thing, or it's using chip SIM cards and tracking trucks and so on. So there are all these use cases, but they sort of started there. But now, of course, that IoT has become almost pervasive, and will be over the next 5 years. I think that's where the real opportunity lies, and that's just the rising tide and the boats model where everybody benefits. I think telco and everybody else.
No, and I think you're right. That's interesting because churn obviously is one of the biggest metrics that the telcos face, or that they follow, I should say. And if they can predict, I guess, based on certain activities, when someone's going to potentially leave them, then that would probably be a very valuable thing. Then. Yeah. Well, what's okay? So that's kind of your business bio. What's an interesting fact that most people don't know about you, though?
Right. An interesting fact which I've been involved in for the last 2-3 years, and it also tends to be aligned to what I'm doing here. I'm very deeply interested in teaching computer science to young people, to kids, and I use this idea specifically to say computer science as opposed to programming. And when I say that I'm interested in it, I've run trials all over the world with young people in the US, also in Miami, in Amsterdam, in the UK. I've spoken to experts from everywhere in the world, from Israel to Holland and so on. And
Nice.
what I'm going to do now over the next 2 or 3, actually literally next month or so, is I'm going to launch a Kickstarter, which will be more an open source project to teach data science to young people. And that is a very interesting challenge. And to do that, what we've done is we taken feeds from the NASA Phoenix mission, and we then use those feeds to predict certain things. And I think that I like this whole idea. I have a genuine passion for it. I work very closely with my son. My son is sort of mildly on the autistic spectrum, and we're deeply interested in computing, and I've always been interested from that perspective as well. So I think space as a concept unites humanity, and I think that that's something. It's a great way to get kids interested in the intricacies of data science.
No, I agree, and I think it's going to be somewhat of a challenge to get them interested. But I think if you choose a really cool, I guess, use case, then that'll certainly go a long way.
Exactly.
And I think if you look at, there are certain initiatives that are going on in the field of IoT today that are looking at the workforce, and they're looking at what the requirements are for the workforce. And while you're super qualified being a data scientist, one of the things that everyone has identified is that there's going to be a huge need for more data scientists. And so if you can convert some of those kids to computer scientists first, and then maybe it's a data scientist after that, I think that would be very well served. You would be very well serving our industry. So do you have that information? We'll ask you. We'll put it in the show notes if you have it now. Otherwise, I'll get it in there after the fact.
Well, it is. Yes, I mean, I have to wait for it at least, hopefully, maybe the next week. And the reason I say that is because I'm working with some leading data scientists all over the world, and I'm going to make it into a more collaborative and a philanthropic venture. And while it will be Kickstarter, but it will also be get inputs from data scientists all over the world onto how data science can be taught in schools, and then they're going to completely open source the whole thing, so that anybody in any part of the world can take the whole thing up, translate in their language, and off they go. So it's a truly a passionate project of mine, but I have to just wait till this week. I'm waiting because 4th of July, as you know, was a holiday in America last week, and I'm just waiting for a couple of people to get back from holiday before we declare this. Yeah.
All right. Well, very interesting. I'd like to expose it to my teenagers anyway.
Absolutely.
They're not kids, but they're teenagers. All right. So let's continue on the data science. So I think a good place to start, at least to clarify things, is what is data science, and how would you differentiate it from statistics or analytics, or are they all the same thing? Maybe you can, Ajit, you can help us out with that.
Yes, I mean, the statistical framework has been around for a very long time. So if you look at Bayesian methodologies and so on, they've been around for hundreds of years, literally.
Yes.
And also statistics as a field has been around for a very long time as well. Now, what has changed really is, I guess, 3 things. The first one is the fact that we have very good, firstly, we have data. Yes, I mean, we have tons and tons of data.
We got lots of it, yep.
And that has literally been over the last decade or so. The second aspect of it is that we have very good CPU power, and also the whole big data paradigm, which is essentially parallelization. So if you look at any of the big data vendors like Cloudera or Hortonworks or Mapar or things like that, the whole Hadoop paradigm is all about splitting across different processors and then parallelizing the work. So therefore, that has been the second aspect which has brought data science to the forefront. And the third one has to do I said the CPU, and then the algorithms themselves. Now, the algorithms, while they have been around for many years, so specifically the deep learning algorithms, for example, they've been around for a very long time, but now all these other factors make them possible. The CPU especially makes it possible to implement these and bring the results back in a reasonable time frame. And that really has changed things. Now, there is one other thing, sort of a caveat in this way, that has to do with machine learning versus data science. Now, machine learning as a paradigm is all about computers learning from experience. Yes.
Yep.
And that involves a whole bunch of telling what is spam versus not spam, what is cancer versus not cancer, and that kind of use cases, which a machine is given enough instances of positives and negatives. The idea being that the next instance they see, which is not classified, they are able to do that classification or the clustering and so on. But the intelligence of a machine is based on the training and the learning which has gone on before it. Yes.
Right.
And this is where the whole machine learning paradigm goes through. But the data science is a wider thing. So data science involves the whole idea that you get the data, you make a hypothesis, you apply the model, which is the actual machine learning algorithms, and then you do the visualization, and then you do predictions and so on. So data science as a discipline is often less sexy than people think of it as, because there's a lot of work involved in just getting the things together. And I come from a data warehousing background many years ago, which in the data warehousing world, this was called ETL, which was called Extract, Transform, Load. And that was where you did all your work, because once you actually managed to get it into a denormalized structure, then you basically then did some kind of a high-level visualization like Cognos or business objects or something like that, and then it was all kind of good-looking, so to speak.
And that's the unsexy part you're talking about,
exactly. Right? So is the equivalent of that ETL is what I'm talking about, and which is where a lot of the sort of the grunt work of data science gets done, and that doesn't change with anything. I think that's the only difference with data science is that you need to know a lot of the predictive stuff as well. So,
but Ajit, what I want to ask you though on that, ETL is alive and well in IoT in many circumstances, but in some cases, what about the situation when you're bringing the analytics to the data versus bringing the data to the analytics? I mean, is that something that you're seeing today, and how is that different? I mean, or is it still an ETL just in a different form?
Well, I think that what happens with ETL still happens in many cases, but the real difference with data science, and I bring to my personal thing, has to do with real time from my perspective because of IoT. And that's where the ETL model isn't as directly applicable, because there's a lot of streaming data, a lot of real time data, a lot of sort of windows of data you want to work with, and so on. And the tool sets have changed as well. So the entire the big data tool sets, the Spark and Storm architectures tend to be more on real time, whereas the historical MapReduce paradigms are almost not directly applicable to what we are trying to do in IoT. And I think that this is where there's sort of a long way answer to your question. But I think in real terms, a lot of these vendors are also merging things together. So you see big data vendors which were into data warehousing get into big data. So I think those sort of the boundaries are becoming blurred.
So when we talk about data science again, you said it's bigger and it encompasses machine learning, for example. It's a little bit wider. Does it also encompass then, the other, analytics in general and statistics? Are these just all subsets of what data science is?
No, so it encompasses those disciplines, and specifically they get implemented as what we call models, data science models within machine learning. So, for example, if you use Python, if you use Python as a data science tool, then there's a library called scikit-learn, which is what is used to, and it has regression algorithms, clustering algorithms, and all those things. So when you actually implement these things, they are function calls or library calls or Python libraries. So it's not that hard in that sense. So it's not, the programming is all about understanding what's out there and how to use that. The challenge is in understanding why that is being done, and what to use and what not to use and what to do before, and how to reduce the dimensionality of the data, how to use the data sets, how to train the data set, that kind of stuff.
Okay.
So it's that's where the data science gets much more, because data science is not an exact science, and this is where I think a lot of the current discussion around robotics and all these sort of ethics are going along, because a machine is only as intelligent as you train it to, and you train it using data, and data is subjective. So it's not like if I take an apple and drop it, it will drop every time. But if I have a machine which is make a certain prediction, that prediction depends on how I have trained it. And in doing so, there is a subjective bias to the data I have chosen to train it and chosen to ignore and chosen to summarize to a higher level, ... So that's what I mean by that.
Okay, so I think what you're saying then is statistics and analytics, these are tools that you apply, but the real art or the real science in data science is how you apply those statistics, what statistics you choose to apply, how you apply those analytics, and what types of analytics you choose to apply. Is that maybe a good way of paraphrasing?
Yes, I think so, yes. Yeah.
Okay, so that takes us into data science for IoT. Now, we've had traditional data science, as you've mentioned, for a long time, but what would be the difference between data science for IoT versus traditional data science?
Yes, I mean, there are a few differences, and they are some of them are obvious and some of them are not. So, for example, if you're a traditional data scientist, you wouldn't muck around with hardware, for example. Yes. So by that I mean, I literally mean that. So if you talk to Cisco and Intel of the world and so on, they all talk about computing at the edge, cloud computing. Sorry, not the edge computing or things like that. And they all, in many cases, mean that you are taking data but not sending the whole thing back to the cloud. You are doing some processing at the edge. And therefore you're sending some kind of a summary back to the cloud. And this paradigm is very different if you are a traditional data scientist, because you are used to working everything with the cloud. The second thing is that, so for example, the other bit is a lot of the real-time processing, a lot of the edge computing, a lot of the cognitive in-memory processing, and also the nature of the data itself. So the nature of the data is time series data quite often. So it is like smart metering and so on, mostly time series data, and the scale of it as well. So I think that at the moment, I think you and I would agree that IoT, the full impact of it has yet to be felt, and will be felt over the next 5 years. So in my view, the IoT data sets would go much bigger over the next 5 years. And also, in addition to that, and the reason I say that is because I think that IoT will include both the local area and the wide area connectivity. So at the moment, we have a lot of the connectivity being driven by Bluetooth 4.0 or its ilk, yes. And then if you consider the next 5 years, then you consider the 5G, which is around 2020. So I'm not saying that we will have 5G in 2020. I think that's always been, telco cycles have always gone, sort of taken a bit longer, but maybe a little bit beyond 2020. And then you have both the local area and the wide area connectivity for IoT devices. And that truly takes us into ubiquitous IoT world, which has been the dream over the last 99, or was from the year 99, or whenever ubiquitous computing was designed. And therefore, I think the big opportunity is over the next 5 years. And that would really make a big difference to that.
So I think what you're saying then is data science for IoT. You're saying, well, there's definitely that real-time component of it, and that's doing it at the edge. And like you said, whether you're using something like Spark or Storm, you're dealing with some form of edge computing because it can't be done in the cloud. Then you're saying, the type of data, well, it's all pretty much the same. It's all going to be time series, and so we want to and you were talking about parallelization earlier, but whether we're doing it in real time or whether we're doing post-processing, it requires certain types of algorithms that are going to be able to parallelize the data in such a way that you can isolate certain components of it and focus, in real time on the areas that you care about. And then related to that, you're saying scale, and you're saying IoT is just producing lots and lots of data. And as you and I, what's the statistic? I keep hearing different statistics, but I understand at a high level, we generate, let's say, 100% of data, but we only use, in general, on our average, we only use, 10% of that data that we capture? Or is it even less than that or more than that? Do you know?
No, I've heard more statistics as well. I think, and I think that is right. I mean, but let's say that we use a very small percentage of the data, and I think, but it also brings me to another very important point here is that I consider the whole data science for IoT to be the key business model behind IoT. And the reason for that is because, in my view, I think just about everything is becoming commoditized and open source. So if you look at hardware, there's a lot of open source hardware at the moment. So if you look at Arduino, Raspberry Pi, and so on, if you look at the software stack, that's also the same thing as well. And that would then leave you to sort of your value is not in data as well, because there's a lot of open data, and open data is great, but it's a level playing field, and it means that your value as a company or a startup or a business model really is in the analytic, which is your essentially your secret sauce. And the beauty of that, of course, is that it is the more it is used, the more accurate it is. And the better it is at making future predictions. And that's why I think that's the key differentiator.
Yeah, well, Ajit, you and I are on the same page, on this. I mean, I teach everywhere I go that same thing. I maybe say it in a slightly different way, but all incremental value of an IoT product or process or environment is all in the business information that you get from it. And how do you get that business information? You're getting it from analytics. And I agree very much. If you talk about the commoditization of just technology in general, we definitely have it on the hardware side where there's the small endpoints, although sensors are, you could argue that's obviously still has unique intellectual property, but definitely on the endpoints, and then at the core, even the servers are open source. And now if you look even in your world of data analytic tools, a lot of them are open source, if not most. Well, I won't say most, but a lot of them are open source. So if you look at it from a company's perspective and you look, where is my intellectual property as a company, it's going to be there. It's not going to be in the plumbing. It's not going to be in the sensors, because unless you're going to become a sensor company, it's not going to be in the networking, boxes, unless you want to become a networking company. It's going to be how you apply that data science to the data that you have and with the other sources of information that you have, so you can create some value and then create some, some actionable, intelligence based on that value. So absolutely. I agree 100%. And, from a business point of view, that for anyone that's been listening to the show for any, period of time, they know that's where the action is. We started technically in this show from the endpoints, working our way up to the data, but this is where the action's at. Why? Because this is where the value's at. So I like it, and we're on the same page. And we're going to be spending a lot of time, on this show, on the analytics, on the data science, just because it's that important. Yep. Now, the machine learning. I hear machine learning. You've given us a short definition. Your definition was that if you give the machine, the algorithm, the software, enough circumstances of a certain condition, they'll record that, and then based and as they have more and more of these conditions, they'll be able to give you more and more accurate, I guess, predictions based on what the next data point will be. What's the state of the art? I mean, you hear that. Is this just like is this like a buzz term right now? I mean, obviously it's been around for a long time, but what's the state of the art in IoT for machine learning?
Well, I think partly because it's been a buzzword, but I also think that it has a real value, because most of these things are based on simple predictions, and there is no real sort of a limit to what you can do. So there's lots and lots of things you can combine to make a prediction. So, for example, IBM has a very good use case which was to do in China, and they predict street level pollution in Beijing, I believe, 3 days in advance. So it's a street level pollution in the city 3 days in advance. So to do that, it requires you to do a lot of processing and merging of many different data sets. So there is a traffic, for example, there are specific sensors, then there is weather, then there is maybe some other industrial output, maybe there's holiday time frames, and so on and so forth. So there is a lot and lots of different things which kind of build on top of each other, and to make a prediction, they really merge with each other, and that's why this area is very complex. So it's not. So that's why I started almost with sensor fusion, because that's really where the world is sort of going. The second very interesting aspect here is what is called deep learning. So deep learning is again the cutting edge of IoT and data science. But from my perspective, I'm interested in deep learning in the case of IoT because I consider cameras and images as sensors. So
I agree. So, but what is deep learning, though?
Yeah.
Like, what's the definition of deep learning?
The definition of deep learning is, if you think about it on two ways. So firstly, the motivation of deep learning was to mimic the brain, to mimic how the brain works, and to use different layers to make a prediction. But a real definition is more the latter, what I said. Rather than mimicking the brain, it's more like you use different layers which feed up on each other to make a prediction on something bigger. So a good example of deep learning is Google's example of identifying cats. And the way that works is that you show a computer lots and lots of YouTube videos of cats in them, and a computer doesn't know anything else. It just identifies an image from a video. And literally the way it works is that it works bottom up. So it identifies pixels, it identifies edges, and so on until it finds objects in a picture. And in doing so, what it does is that it's a mixture of supervised and unsupervised algorithms. So it starts bottom up. It doesn't know anything about anything else, but identifies sort of things which might look like cats. And then you tell then you tell the algorithm that this is indeed a cat, and then it replays itself, and subsequently learns from these images, and that is possibly the most interesting example of deep learning. The other being more recently was a computer which was taught to play Pac-Man. And also a computer which was taught to play a few other games by looking just at the gameplay and the scores, rather the images of the gameplay and the scores, without understanding, without actually training the computer about what it is doing. And in doing so, of course, that what is interesting here is that the machine is learning like a child would learn. And a child learns by observation. And a machine learns, and a machine which learns by observation suddenly becomes a very interesting paradigm. And that is why you suddenly have a lot of discussions about AI and sort of the morals and ethics of AI in the discussion in the media sphere for the last year and a half or so, because I think this was not on people's radars, that people didn't think that computers are going to get that smart enough, and now they do.
Well, yeah, no, I mean, I was going to say it did sound like a lot like artificial intelligence, but I'm still trying to clarify the difference between deep learning and machine learning. And I think what you're saying is the type of algorithms that are being used. With deep learning, observational algorithms and other algorithms are being used versus maybe more statistical, or I don't know, versus different algorithms being used in machine learning. Is that, how do you differentiate the two?
Well, in the end of the day, they are all algorithms. When you say machine learning, well, deep learning
versus
is perhaps,
deep learning.
Yeah, well, deep learning is perhaps an extreme form of trying to understand machine learning, where you have a problem which is minimally defined, so to speak.
Okay.
So there are no rules, and there is.
That's a good definition, though.
Yeah. So there is what is called a sparse data, or rather the problem set is an infinite problem set. So for example, if you think from a computer's point of view, that teaching a computer to play chess is quite easy, because the problem domain is finite, because there are 64 pieces, there are X number of characters, and they all have a certain movement, and it's all well defined. But it's not the same as teaching a computer to identify a cat or a dog, because there are different cats and dogs. And for example, there could be it could be a boxer or Doberman Alsatian. It could have a collar. It could be a puppy. It could have its ears cropped, kind of stuff. So just by the problem domain becomes extremely complex. As opposed to, and that's the sort of problem where you need deep learning, and the beauty of that, of course, is becoming more and more interesting in terms of the CPU capacity. So Qualcomm in the Mobile World Congress had a demonstration with a deep learning algorithm on a phone, where it was able to identify things looking at through a phone. So I think these are becoming more and more pervasive, again, with data, algorithms, and CPU. So if you look at a company like NVIDIA, for example, yes. So NVIDIA historically was making chips for games. Exactly, yeah. And now their stock price has gone quite high because they have a brand new business domain, which is deep learning chips. And that's a huge domain, and that's where I think you need specialized hardware to do these calculations. That's where it's all going. So that's how I see those areas. Yeah.
Yeah. So deep learning. I mean, obviously, there's still a bit of work to be done, as we've seen by Google trying to identify gorillas, but in general, it's moving forward. But another question I have, though, is when you describe machine learning, it sounds a lot like predictive analytics. What's the difference, or are they the same?
Yes, I think those two phrases are being used interchangeably.
And they should be used interchangeably?
I mean, it depends on how much how widely you define machine learning. So what I mean by saying that, when you say predictive analytics, the predictive analytics is used to make a prediction of some kind. Yes. So if you have a machine learning system, it ultimately makes a prediction of some kind, but it is in general a system which is learning from experience. So if you think about Nest, Nest, N-E-S-T, the Google's owned by Google now, the smart meter owned by Google. Yes. So if you think about Nest has a machine learning component because it is constantly learning from experience, but it is not making a prediction every time. time. So it's a subtle difference, but that's what I mean by that.
Okay, because predictive analytics, obviously by definition, they're going to be learning from experience, history as well. But what you're saying is with machine learning, you're saying predictive analytics is machine learning, but machine learning is not predictive analytics because it could maybe be using the learning for a different purpose, perhaps making the model better. For example,
that's just my off the cuff reaction to the question, and that's how I see it. Yeah.
Okay, well, I mean, we're on a roll here, so I'm going to ask you another one. I'm asking all these different, I guess, buzz terms or buzzwords, but cognitive computing. I mean, again, cognitive computing versus machine learning versus. Explain, what is cognitive computing then?
Yeah, the cognitive computing idea is very closely tied to the deep learning ideas I just mentioned.
Okay.
So I think that the word cognitive computing is very much in that in that domain, the deep learning or things like that. Cognitive computing is popularized by IBM in quite a big way. So it perhaps is perhaps word used like Cisco thinking of Internet of Everything or something like that.
Okay.
But when people talk of cognitive computing, in my mind, I think of Watson, IBM's Watson computer, which was again the driver behind the Beijing example I just gave, which helps to make a prediction based on a sort of large complex data sets.
Okay. Well, I mean, so this show is obviously, we've been talking technology forever, but believe it or not, it is about the business of the Internet of Things. And so how do we use, let's say, deep learning, or are the practical applications of deep learning, or let's say cognitive computing, if we're going to use the IBM term, for business? I mean, what are the practical applications of this? Or is this something that really is on the fringe that probably, 99.9% of our listeners will not be having to worry about?
Oh no! I think just about 100% of people would have to worry about this, and it's mainly to do with the fact that that is just a way of using data. And all these things are just ways of using data, and whether that data is so when we are talking about deep learning, we're talking about maybe image data or video data or something like that. When we're talking about machine learning in the context of IoT, we are talking time series data, and so on. So all of these things are, at the end of the day, just ways in which you apply to different data sets, merge different data sets, and make a prediction, they apply to everything from wearables to everything else, and that's how they are very relevant, very relevant in terms of things. Yeah.
So from an advice point of view, so if we were giving advice to the business person listening to this show, what you're saying is keep on top of this, be aware of what it is. There may not be an immediate use in your business, but you should definitely be keeping on track of where this is going, or do you have different advice?
My advice is again that I think I see it as a differentiator. So I see it as the fact that there's going to be lots of open data, there's going to be lots of data in general, there's going to be open source hardware and software and so on, and somehow someone's got to put it all together and make it do something which solves the real business problem, and that's where this all comes into play, because this really ties to a specific business problem. So the example of cats I gave you, yes, and that can be translated to identifying cancer, for example, based on X-rays. So think about lots and lots of X-rays of tumors, and this is a real example. So there's somebody trying this out actually, a medical center, and they essentially train a computer based on these images to predict whether a certain tumor looks malignant or not, and this is it will just grow. These applications will just grow because they solve real problems. These are problems which human beings can't solve very easily because the rules for these problems are not very well defined. And a computer, given enough CPU, given enough data, given enough time, can make a prediction which is game-changing. And that's where it comes from. The caveat here is that it does require a lot of processing power, and it does require a lot of data to make a real good prediction, and that's why the big companies are so deeply involved in it. Specifically, we're talking about Google, IBM, Facebook, Microsoft, those sort of guys. And because it is a game where you have to have lots of CPU, lots of very, very smart people, lots of data, and it moves. It changes very rapidly. This is why I think that from a startup's perspective, it is interesting, but then again, you have to perhaps look at a specific space where you are able to make a difference. And that generally would tie to having an edge in one of two areas, either a CPU edge or a processing edge or a data edge or something like that, or algorithmic edge.
Yeah, and for a startup, I would think algorithmic edge would probably be the winner on that case. Okay, exactly. So what you're saying is, what you're saying in general is, of course, data analytics or data science is super important. However, there's a class of problems, and this is an underdefined or underdefined class of problems where you don't have enough data to make some quick rules, use rules to make assertions. So in that class of problems, you're saying deep learning or cognitive computing is very important to be able to solve those type of problems. And it's something, if your business is focused on there, whether you're trying to observe if chips are coming out of the fab in the proper shape or identifying different, cancer, growths, then cognitive and deep learning has a place, has definitely a place in your business. Yeah. Okay. So, I think this has been a useful conversation just because there are so many of these terms. We've covered a lot of them, data science and analytics, statistics. Obviously, I think we've got that kind of figured out. But the machine learning and the cognitive computing and the deep learning, I think, are all things that are thrown around a lot. And I think it's useful for the listeners just to, have a pretty good understanding of at least at a high level, like I do now, understanding of where they play. Cool. Okay, Ajit. Well, that was really helpful. Now, how can people find out more about you, what you do, what your company does? Feel free, just to let us know where people can find you and learn about more what you're doing.
Indeed. So at the moment, the most, as I mentioned to you, I teach at Oxford University, and this is exactly what I teach. So I'm teaching data science for IoT, and what we are doing is we have a course at the university which is mostly at the moment not yet launched. It is mostly for corporates or still under testing. And what I do have at the moment is we have a course which is launched in London and also online, which is really the same thing. It's called Data Science for the Internet of Things, and I will send you the link, or I've already sent you.
Nice. We'll put that in the show analysis notes. Yeah.
And what we do really is exactly what I just mentioned. So we have a practitioner version and we have a strategic version. So if you look at the practitioner version, this is all about building something, creating a project, and actually looking at the programming and the mathematics. And the strategic version looks at all the things without actually the programming and the mathematics behind it. And we had a great response. We had lots of startups, lots of interesting companies and individuals who want to really sort of go out there and do things. And it is a full data science course, but because it is based on a vertical, which is in IoT for us, it allows us to take an engineering-led approach, which means that rather than starting from algorithms, you start with a problem. You start with a physical thing, just like the example I mentioned to you about the old people's home and things like that, which is cognitively easier for people to grasp.
Right. It doesn't have to be as general.
Exactly. Then they see that something's happening. Then they see how they can solve the problem, as opposed to talking about regression, clustering, and so on, and then wondering where it all sort of gets applied to. So it is an experiment in the sense that it has never been done before, but it's getting very interesting responses. That's what I'm doing at the moment. Yeah.
Okay. Well, I mean, I went to the link, and I think you mentioned that it's an online or will be an online course, but I didn't see how you did that. I mean, has it been put online yet? Is that something like, for example, I could take? I mean,
yes, it's pretty much online at the moment. So what we do is we have a Moodle software. So it's a classic e-learning package, and it's video based. The only difference is that it's not like a classic MOOC, so there are not thousands of people. It's a very small group of people, and I think I work very closely with them because it is quite, like I said, it's all very new for everybody. But it's no different from any online learning platform.
All right.
Yeah.
All right. Well, again, I'll put that information in the show analysis notes. So for anyone that's interested in taking the course, getting involved, and they'll have the information there. And other than that, Ajit, I guess we'll see you in early October in Berlin.
Indeed. Thank you very much. I saw that you had a lot of people at your session there in the Moscone Center. So that's really quite inspiring. So I would have liked to come and sit there as well, but obviously I was next door doing my own stuff. But in Berlin was really.
Well, we'll have a little bit more time to compare notes then. So,
Indeed.
So thanks a lot.
Thank you very much.
We'll talk to you soon.
Okay. Take care. Thank you. Bye-bye.
Okay. That was an interesting talk with Ajit Jaokar of Futuretext. This podcast goes vertical, deep diving into different topics each week. If you prefer a more horizontal and structured approach to learning IoT business and its orbiting technologies, check out my book IoT Inc., published by McGraw-Hill, or become a certified IoT professional by completing the ICIP training and certification program. For details, just go to www.iot-inc.com. Also go to www.iot-inc.com for an analysis of this episode, links to things that were mentioned during the episode, and very importantly, the episode's PDF transcript. Just search for the name of the episode or the guest. If you're new to this podcast, subscribe. That way you'll get every week's episode delivered straight to your device. Or, if you've been listening for a while, there are 3 ways you can support the show. You can leave a rating or a review on iTunes. Just go to iot-inc.com/iTunes. It only takes 1 click to leave a rating, a little bit longer to leave a review. You can share it on social. I'm on LinkedIn, to a lesser extent on Twitter. And of course, you can support the show by buying my book, IoT Inc., or the ICIP training and certification program. It's how I pay the bills. Next week's episode is Data Analytics, Step 2 in IoT Deployments. And that's okay. Not with me. I hope you can join me then. I'm your host, Bruce Sinclair. Thank you for listening. Until next week, may your path to IoT business be a scientific one.
You have been listening to the IoT Inc. Business Show.